Hello, it's Mr. Doro. Today's lesson is going to be dealing with gas laws. And gas laws are just simple mathematical relationships that deal with characteristics of gases as they're changing. Today we're going to be talking about these first three right here, the Boyle's and Charles and Gay Lussac's law, Avogadro's law and ideal gas law. Ideal gas law we'll definitely talk about later, and Avogadro's law we'll talk about some in class. Something that we have to remember when we're talking about gas laws is that we're talking about all substances that are in the gaseous state. We are not talking about gasoline, but we are talking about any type of gas, and they all follow these gas laws. And even with this little cartoon right here, with this gassy guy, these gases would follow the same gas laws that we're going to talk about. There are variables that can change with gases, and the gas laws deal with those, some changing and some staying the same. The variables are pressure, volume, temperature, and number of moles. The first one is going to be Boyle's law that we're talking about, named after Robert Boyle. And this deals with how pressure and volume change with each other when these two are held constant. And that should be in your notes. The constants are temperature and the number of moles. As a little side note, the number of moles can only change, this is the number of moles right here. This can only change if you add gas to it or you take gas away from the container. Otherwise, the number of moles of gas stay the same, but pressure, volume, and temperature can change without even adding gas or subtracting gas from it. Now, if you look at this chart that's on here, then this shows how pressure and volume are related to each other. And so you can see that as the pressure is dropping, then the volume, as we go, if we pick a spot, maybe this spot right here, has a higher pressure but a lower volume. And if we pick this spot over here, it has a lower pressure but a higher volume. So that is saying that pressure and volume are inversely related. As one goes up, the other one goes down. That's what this little formula means right here. Pressure times volume equals K, a constant. So anytime that the pressure would have to go up, the volume would have to go down to equal the same number each time. This illustration shows Boyle's law in action. And so you can see you got the skinnier guy on here, and this is filled with a gas, and it has a certain number of molecules of gas or particles of gas. They should all have the same. I think when I counted this one, it had one extra, but the number of moles should stay the same the whole time. This guy's a little bit heavier here, and so he's putting more weight on this, which is compressing these more. It changes the volume. The volume is less, which means the pressure of these little particles that are hitting each other in constant motion and hitting the side, the pressure is going to be greater because they're going to have more collisions with each other. And this one right here, since the volume, with the bigger boy on it, the volume is decreased even more. There's going to be more collisions and a greater pressure being pushed on each one of these. And that's what Boyle's law shows. The greater the volume, the less collisions with the sides and each other. That means the less pressure. The smaller the volume, the more collisions there are going to be, and the greater the pressure. So based on that information, Mr. Boyle came up with a formula that relates pressure and volume if they change with each other. And so that's what this is right here. We had P times V equals a constant. Well, then P1, the initial pressure times the initial volume, would have to equal the new pressure times the new volume. So he came up with this, P1V1 equals P2V2. And so really it'd be better written like this, P1 with the subscripts, P1V1 equals P2V2. And that is Boyle's law. And so that's what you should put for Boyle's law. Initial pressure times initial volume equals final pressure times the final volume. The next law is Charles' law. And so for Charles' law, we have two constants. It's now pressure is staying the same and the number of moles. We're not changing the amount of gas. I asked this question here, what happens to a balloon when it's taken outside in the winter? And that we know that as it gets colder, it starts to shrink. And so what does that tell you about the relationship between temperature and volume? Well, as temperature drops, then so does the volume. That's called a direct relationship. This graph right down here on the bottom shows a direct relationship. So on this illustration about Charles' law, we have a gas that's trapped inside of these cylinders. And so this gas has a certain pressure, and at negative 65 degrees Celsius, we start to add heat to this. And as we add heat, we heat it up to 250 degrees Celsius. And what we have is the pressure has to stay constant. these are going to move faster and faster and cause a greater pressure. In order to keep that pressure constant, it has to change the volume or expand the container so that the collisions are not as many in here when they're moving faster. And so the volume changes as the temperature increases, so does the volume, which shows a direct relationship. So that gives us Charles' law. The same way that we had Boyle's law, we have V1 divided by T1 in this case equals a constant. So V2 divided by T2 would have to equal that same constant. And so a better, more well-written way would be V1 over T1 equals V2 over T2. Now if you're given any one of these three, you're given initial volume, initial temperature, and final volume, you can solve for final temperature. Or you can, if you're given final volume, final temperature, and initial temperature, you could solve for volume. So you have to be given 3 out of the 4. The next one is called Gay Lussac's law. And Gay Lussac's law has the constants of volume. The volume cannot change, it has to stay the same. And number of moles, the amount of gas does not change. This is Joseph Gay Lussac. And so his formula would look like this: P1 over T1, P1 over T1 equals P2 over T2. Pressure and temperature have a direct relationship. As the pressure goes up, so does the temperature. As the pressure goes down, temperature goes down. Here's an illustration of Gay Lussac's law. You have a gas in a cylinder or a can or something, and that gas is moving around creating pressure. Well, as you start to heat it up and you add a flame to this, they're going to start moving faster and faster, and as they're moving faster and faster, greater pressure, and that pressure could get so great that it could explode. That's why we don't throw aerosol cans in the fire or anything like that, because those gases, we say, well, they're empty. Well, they're not totally empty. It's just that it's equal to the atmospheric pressure. But as you add more and more heat, you get greater and greater, and it could get so great that this rigid container that was rigid, that would not expand, would finally burst, and then you could have a lot of problems after that. So here are the 3 gas laws that we've talked about. One of them with temperature being constant, P1 V1 equals P2 V2. One of them volume constant. You can see on this one right here, the temperature constant, there's no heat being added to it, but the volume can change. This little cylinder can slide up and down to change how much room is in there. This one with the volume constant, it is in a fixed container. It's a rigid container, and so it cannot change the volume, but the heat is changing and the pressure would change also. And this one, the pressure is constant. It also has a volume that can change, and the temperature can change also. And this volume will change with the pressure. The gases are actually going to be moving this pressure or this volume back and forth. So you should be able to match up the gas laws to these 3. So why don't you pause it and see if you can do that to see which one of the gas laws each one of these represents. Well, here they are. This first one is Boyle's. The second one is Gay Lussac. And the third one is Charles. Hopefully you got those right. And notice out of the 4 variables that we talked about, only one of these does not change for all 3 of these gas laws, and that is the number of moles. N stays the same each time. So now we can combine all 3 of these gas laws into really one gas law, and knowing that if one of them is kept constant, then we can just subtract that or cancel it out from there. This gas law right here is the combined gas law, and it is P1 V1 over T1 equals P2 V2 over T2. And so if we know that temperature is constant, then we would just erase or get rid of these right here, and we end up with Boyle's law, P1 V1 over or equals P2 V2. If we knew, let me put that back in there, T1, T2, and if we knew that the volume was constant, then we could say, well, that would cancel these out, and I would end up with Gay Lussac's law, P1 over T1 equals P2 over T2. So the combined gas law, if we can just memorize that, then we can know all the gas laws, all 3 of those gas laws that we talked about, and one of them would just cancel out each time. So here's a typical gas law problem, a type that you might see. And you're asked a 1.5 liter balloon has an initial pressure of 2.10 atm atmospheres. At what pressure would the balloon have a volume of 2.50 liters, assuming constant temperature? So we got to identify some things that we see in the problem here. First of all, from the units right here, liters, we know that liters is a unit for volume. So I'm going to put V above that. From this unit right here, atmospheres, we know that's a unit for pressure, so I'm going to put that. And this unit right here, liters, is another unit for volume, so I'm going to put that too. So we need to find out which one's initial and which one's final. Well, notice this. These go together. A 1.5 liter balloon has an initial pressure of this. These numbers go together right here. Since they go together, these are going to both be the initial, and it says initial right there. It won't always say initial, but these are going to be your initial volume, V1 and P1. They go together, so they have to both be ones, or even they could be twos, but it works out better if you start out with your starting ones to be the ones. And then so this volume right here, the second one, at what pressure would the balloon have a volume of this? This is the new volume, so this is V2. So we're going to use Boyle's law. It says constant temperature right there. Boyle's law is P1 V1 equals P2 V2. And then we plug in what we know. P1 is 2.10 atm. Yes, you have to put the units on there each time. Times V1, which is 1.50 liters, equals P2, we don't know. We're going to have to solve for that. And V2 is 2.50 liters. Now, in order to solve for P2 to get it by itself, we're going to divide both sides by 2.50 liters. 2.50 liters. Cancel these out, and then our P2 ends up being 1.26. That's 3 sig figs. And this one didn't need scientific notation anyways, but gas laws, I do not require scientific notation. 1.26, notice this, liters cancel out. We're left over with atmospheres. That's why you write them in there each time. ATMs, and that's my answer. Put a box around it. Okay, this problem is quite a bit tougher, so you really got to follow along with me on this. So, if we look at just the units on these, we know that centimeters cubed is a unit for volume, so I'm putting a V there. This is degrees Celsius, that's a unit for temperature. This is kPa, that's a unit for pressure, kilopascals. But we've got to figure out what else we're given here. It also says STP. Remember, STP is standard temperature and pressure. Standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere, or all those other things that we said it was equal to. In this case, we have kPa's, kilopascals, as our other pressure. So we want the standard pressure in kPa's, which is 101.325 kPa. That's a 5. And that's a P. 101.325 kPa. The other problem is our temperature, which we know that our standard temperature is 273 K. That's T, and this is P. Notice these go together, volume, temperature, and pressure. And so these are all our initial. So V1, this is P1, and this is T1. But this other temperature is in degrees Celsius, and we have to change that to Kelvin. So the way we do that is 273 plus that 95.0. Sig figs get a little bit difficult in this, but we usually go to how many places after the decimal that we had it in Celsius. So this is going to be 368.0 Kelvin, and that was our T. We already had T1 was 273, so this is T2, and this is P2. So we're going to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2, and then we plug all these in here. P1 is 101.325 kPa. I'm going to pause it and write them in. Okay, I've written all these in with the correct units. So what I need you to do is I need you to solve for V2 right here. Get V2 by itself, multiply both sides by 368, divide both sides by 110.6, and then you plug it in, find out what the new volume is and what the units are on it. And here's a little cartoon to brighten up the rest of your day to finish us off about Elvin and the Chipmunks. If you have no idea who they are, then, well, you just keep on moving. But they had that high squeaky voices in there. And so This is all talking about their addiction to helium. Have a nice night.